My name is Daniel Coupal. I've been at MongoDB for a long time, closing on 10 years. I'm currently in the strategic account customer team who take care of doing design review for them with an access on data model. Some of you may know me from my blogs on schema design pattern, anti-pattern, the MongoDB University data modeling class, and numerous presentations I've done that you can see are the common theme. It's been an exciting year for us. There's been a lot of things that have been announced. You've heard some of them this morning, from queryable encryption that put us at the top of the pack for security in databases. Relational migrators just getting better and better. It's been GA recently. And the other one that everyone wants to hear about these days, be able to do queries through an engine that's going to give you results like our AI type by storing all your AI information in the vectors in Atlas. But for me, there's also been a lot of excitement from that book that I published this year with Steve Oberman, a guru in relational databases, and Pascal Desmarais, the founder and owner of Accolade. The collaboration was absolutely fantastic. There are a few times in your life where you get really lucky. That was such a moment for me. And the main lesson I got from partnering with these two people is that you need to get people who complete you, but also understand each other so you can make progress very quickly on things that you don't align right away. So on that, all of you obviously are here because you want to hear about data modeling, so let's get going. So I divided the agenda into three sections. First, we'll talk about the need to model for MongoDB, not just MongoDB, for NoSQL in general. And then we'll present a very clear techniques, methodology on how to model for MongoDB. And then I'm going to spend a little bit more time on that third phase, more particularly on one of the schema design pattern that I really love. It's called the schema versioning pattern. So let's get going. So we need to model because we have constraints. We can have physical constraint. Obviously, if the latency is not zero. If you put your application closer to your user, closer to the database, you will get better results. You also get constraint. Having a little issue here with the clicker. Okay. We also have some hardware constraints. RAM is really fast, but it's expensive. And on the other end, you have disks. They're cheap compared to RAM, but they're really slow. So you need to deal with this dichotomy of resources and understand them in order to do efficient models. And finally, there's also constraints that come to you in the form of software implementation that needs to work with these underlying constraints. For example, when you deal with MongoDB, there's a maximum document size that you'll be faced with. And also, there may be some functionality that do not exist in MongoDB or did not exist when you started your model. So that brings us to the first principle, is we model to face and answer to constraints. And the one we're interested to talk about today are obviously MongoDB. So if you look at the layered application, you have your application talking to MongoDB, who talks to the hardware. And what's interesting about features is some of them have been there forever. When I joined MongoDB, obviously, document models always been there. There were indexes, very rich indexes that let you index any part of the document. And sharding, replication, all that's based into MongoDB. However, there are a few things that didn't exist. We didn't have transaction. We didn't have field-level encryption, or what we call queryable encryption, the new version now, data federation, archives. So a lot of good stuff has come over the years. But that doesn't mean that you couldn't model without those. The difference is you would have modeled differently. So for example, we didn't have transactions. You could mimic a transaction by doing a double commit. Now, obviously, using a MongoDB native transaction, it's pretty much like doing a SQL transaction. It's the syntax pretty much the same. Same thing for something like field-level encryption or queryable encryption. You could yourself try to manage the keys, encryption keys on the server, encrypt things yourself, send them to the server, get the result, decrypt, and everything. But it's kind of heavy. And if you use the MongoDB feature, we do it for you. And we also can do additional stuff on the server that you wouldn't really have access to. And same thing for other functions like data federation, archive. You could archive to another cluster if you want. You can archive to S3 storage. You have to write your own code that's going to once in a while run and move things around and all that. Use Atlas. With the online archive, everything is managed for you. And regex, now we do offer Atlas Search. You don't have to deploy your own Lucene database. So the point I want to make, it's imperative to know the features of the product you use. When you know those features, you'll probably model differently. If you don't know them, you may not model the exact same way. Now, what happens when you model a certain way and a feature happens after? Well, you'll be in a situation where you may want to adapt your data model. And that's what we're going to cover in the last part of that presentation. So let's build a little application here. We're going to call it a social network for chefs. The chef's going to be writing some articles, recipes, and other stuff, maybe describing a restaurant. And we're going to have a need to categorize and tag all that information. And then we're going to get some users coming in and wanting to consume that information. They're going to read it, and some people may comment on it. If I give this problem to all of you here and ask you to do a relational model out of it, well, most of you will probably come up with that solution. If you want to respect the third normal form, that is the only solution. Now, you may want to do optimization later. It's going to look a little bit different. But the point I want to make is, between pieces of information, once you've established what their relationship cardinality is, it's 1-1, 1-to-many, many-to-one, many-to-many, but it's given. It's the same thing. Regardless if you're in a traditional relational database or you're with MongoDB, you have the same relationship between the piece of data. Now, if I ask you to model from MongoDB, well, you may end up with a solution on your left-hand side, which is you're going to say, oh, the main thing I'm playing with is articles. So I'm going to create a collection of articles, and I'm going to put all the information in it. So everything will be embedded. Note that the one-to-many relationship has been embedded as an array. So in MongoDB, in the document model, an array is basically the instantiation of a one-to-many relationship. Well, looking at this first solution, people may say, you know what? If someone is writing many articles, we're duplicating the information about that person in that people section. And I don't like that. So I'm going to extract the people. So I only have like one document for a given person. And that person can write many articles. Yeah, that's good. If I ask you what's the best solution here, well, some people may say, I really don't want to have that duplication. I don't want to deal with it. So I'm going to go with one solution. But there are cases where that application is acceptable, the data is not going to change, and it's going to give you better performance because you're doing only one read instead of two read. Maybe you divide your hardware by 2 just by embedding those 2 pieces together. So that's a lot of saving. So that goes back to the question, which one is the best solution? Well, the answer to that, it depends. That's the answer to everything. I see. But OK, let's be a little bit more precise. So the optimal grouping of objects into collection is determined by the workload. And that's going to bring us to the next section. So what we've established is that the workload is really important. And this is not just because it's MongoDB. It's because it's modern application, modern databases. The needs to support terabyte of data, it's something we didn't have before. So if we didn't have the best performance, we didn't really see it. But now when you deal with that amount of transaction data and all that, any little improvement can save you a lot. So what we're going to propose here is a methodology in 3 phases. As I said, the most important thing that you need to think about at the beginning is going to be your workload. Once we know that, then we're going to know exactly what we want to do. We're going to move and establish relationships. And then finally, we're going to apply the pattern. So patterns are going to be kind of this special sauce that's going to give us extra performance. So for those of you who are coming from the relational world, you probably see here a little pattern. It's like, hey, when I used to work with relational database, the first thing I would do is an ER diagram, and then we'll be writing the code, which is ineffective, like trying to identify the workload. And if something was slow, we would denormalize and do something. Well, with MongoDB, we do the opposite. really want to identify the workload first to be sure that we get to match all the requirements for performance. And only when we have that, we can be sure we're going to get a better data model. So understanding the workload, what does it mean? Well, it means, besides the data, how many objects are we going to get? How big are they going to be? How much space I'm going to need for all that? What's going to be the type of machine that should be needed to support all that? It's going to be about quantifying the operation. Do I have a write workload? Do I have a read workload? What's more important? If it's read workload, is it going to be the number of operation I'm doing per unit of time? Is it going to be the latency that's going to be the most important? And then we're going to put numbers on that. But there are cases where you have things that you're not putting numbers. So that's going to be about qualifying the operation. Maybe some of the data has to respect GDPR, for example. Maybe you have requirements for archiving the data. You need to keep it for 3 years hot, and then an additional 7 years in an archive. So once we answer all that, we're going to get a much better understanding of what our system tries to do. So here's an example back to our little system we're trying to design here. We're going to have two types of write operation. Let's say that we have the chef coming in, writing new articles. I don't get a lot of those per day, maybe 10, but they're very critical. That's really the essential piece of the system. So I want to be sure that there's no issue there. Then we're going to have people writing comments, a lot more, obviously, than the article, maybe 10,000 a day, so 1,000 per article. Then in the read operation, we're going to have our users coming in and reading information, consuming stuff, a lot more, like 10 million reads a day, for example. And then some analytical queries. That'll be trying to understand what we can do to improve the system, doing sales, whatever, so 10 per hour. So that's not a lot, but those have a special meaning. When you do an analytical request, you go and scan all the data, you bring that in memory. In a huge system, that's a little bit disturbing for the machine that's trying to serve all the queries. So for example, when you use Atlas, we do suggest that you spin a different node in order to isolate these kind of workload that are very disturbing for where you're trying to satisfy some performance. But the key thing you're going to get out of this thing, your main operation, is going to be one or two that probably dwarf the rest. These are going to be the one that you want to design for. So in our case here, it's pretty clear that we get a lot of reads happening for our users. We don't specify our users. We want them to be able to read an article very quickly, not have to wait to assemble it and display it to them. Two things. First, it's going to happen very often. Secondly, I want a really low latency on it. So for that, more important query, what I'm going to do is detail it a little bit more. In this example here, I'm adding the latency, 10 milliseconds. We calculate the whole size, and we do have these attributes about what we're supposed to do with the operation, which is, I want to keep it for a certain number of years and keep it for longer after that in a cold storage data where I'm not going to access it very often. So on the right-hand side, there's a pane here. It's coming from the tool Accolade, something they added recently to the tool that I like because I've always wondered, how can we capture that information and be able to review it later, maybe a year later as it changes? Well, the tool added that for each collection, you can tag or describe some additional operation on it, read, write. Often they happen. And some characteristics like durability and how long you want to keep them, the freshness or staleness of the data that's acceptable, et cetera. So it's very good because it puts information in the GitHub repo, so you can always diff later to see what changed. And the key thing about what changed is we can best act on the new hypothesis if we know the original hypothesis. If you don't know what you're building the system for, when you open, and it has 10x the number of queries on a specific piece of data, well, if you didn't really know what you were modeling for, you really don't really know the impact. So I'm a real pro for let's write down what our main hypotheses are and ensure that we design the system correctly for it. Once we get all that information, we do have a better understanding of what we're trying to do. So we're moving to the next phase, which is establish the relationship. And as I said, it's not because It's MongoDB. It's not because some people call it non-relational. There's always a relationship between pieces of data, and they're the same regarding the system you're going to use. As a matter of fact, MongoDB has different ways to represent the same type of relationship. So, for example, a one-to-many. And this is where you're going to have to answer that question. How do I want to present that relationship? Do I want to embed it? Do I want to reference it? So you get more choice, and that's exactly what you had with the two diagrams earlier. So we need to identify the relationship, quantify the relationship, and why do I put an emphasis on quantify the relationship? In the past, it seems like 0, 1, many was enough. We had all the information we wanted out of that. But when you deal with big data, many may not be the right way of describing something. I prefer using a tuple of 3 numbers: the minimum, the maximum, and the most likely value. And if you put that maximum value, it's going to give you some hints. If you have a relationship that's 1 to many, and the many being 1,000,000, well, you probably don't want to take 1,000,000 sub-object and embed that into one. That object is going to be way too big for the system. And as I said, after that, you need to answer that most important question, is should you embed or you reference? Now, to illustrate how the concept of a relationship is applied in the tabular database versus MongoDB, let's take the example of a car. With the tabular database, if I bring my car home at the end of the day, I'm in the application, and I want to store it in my garage, which is the database, well, you would put all the wheels on one table, the seats on another one, the brakes on another one. You see a little bit of the picture. And the day after, when I want my car out, I'm going to have to reassemble all the parts and then drive away with it. So what's wrong with that picture is I'm always reassembling the same pieces together. And that's exactly what the join is doing when you're doing a SQL query. If you have a one-to-many relationship, that many, every time you run the query, it's exactly the same object that you're reattaching to this object. It's a lot of wasted resources. So that's why we have the document model in MongoDB. You bring your car, you do your write, which is you put your car in the garage, and when you want to use it, you want to use all these things together. You just get it out and use it together. So what is used together in the application is stored together in the database. And if you have to remember one principle when you do your data model, that is this one. Am I using these pieces together? If I'm using them together, don't do 3 reads all the time to assemble. Do 1 read, embed the information. If you do 1 read, and there's a ton of things you never need, you always have a subset. Split the things. That's going to be like the base thing for deciding if you should embed or reference. So just to be sure it's clear, when we say reference, it's very much what you get in a relational database with a foreign key. So in this example, there's me and my driver's license number that points to another document in which you're going to get the information about my driver's license. Alternatively, if I decide to embed, I can create a subdocument. It doesn't have to be a subdocument, but for another entity, it makes things clearer like that. We're going to bring all the information. But we're going to have only one document, all the information together. If it's a system that always needs to get the license number when it's retrieving my information, that's what you want to do. So what are the main rules to decide if you should reference or embed? Well, as I mentioned earlier, if you have a very large relationship, a person is followed by 1,000,000 users, you probably don't want to embed that. You want to reference things, keep things separated. Integrity on the write operation from many to many. So if I have a many-to-many relationship and I embed it, I'm going to create that application in this case. So and if I change a little thing, I may have to update all of them. Maybe I don't like that. Sure, I can use a transaction. You can always use transaction in MongoDB. They're very similar to relational database. The only thing, if this is the main operation you're running 10,000 times per second, do not use a transaction. Okay, you're wasting resources. When a piece is frequently used, but not the other, I have a large document and I'm using this section, but it's very big. And I have a lot of these big documents in memory. If memory is a problem, if I only have 500 of these documents, fine. But when I have 1 billion of them, I don't want to keep all the large document in memory. Split the parts, put them aside, okay? Now, what are the rules that's going to say you should be embedded? Integrity of read operation for the data that's read together. Again, you can use a transaction. But the base of MongoDB is the document model, and the document model is atomic. So when you're reading something, you can be guaranteed there is no writer writing over part of the object. You want to read the object, you're going to get it. So go for it. Integrity of write operation on one-to-one, one-to-many. What you were doing in a transaction in a relational database, I'm updating that, and I'm updating a one-to-many relationship. If those things are together in the document model, you don't need a transaction, because you just have to write the update to that document, and that's it. So it's going to be much more performant. The next one is something I discovered like this year working in this team, data that is deleted or archived together. We do a lot of work with financial institutions, and they have this need to archive data. But in a relational database, when you try to archive data, it's difficult because you would have to archive all the pieces from the join that you want to do in the future to reconstruct that data. So all the pieces have to be archived at a given time. You're thinking more data warehouse. It may be a little bit complicated. But with MongoDB, if you structure your document, that it makes sense by itself because it has the user with its address and the transaction and all that, into one piece, you can archive this document. You can go read it 4 years later, and this document by itself makes sense. So that may drive you to model things a little bit differently so you can retrieve all that information at once. And finally, by default, embedding is usually much simpler. It matches the code that you have, so that's what you should prefer. Something I came up recently, and it's in the book, it's a bunch of questions, so it's a bit orthogonal to that. But that should help you a little bit decide if you should embed in reference. So I've created a bunch of questions, and you answer yes, no, so you circle which one it is. And by the end of the exercise, if no, everything is in one column, it's pretty clear. You should be embedding. If it's in the other column, you should be referencing. If it's in between, it's a good indicator that you may want to apply a pattern, which is going to be in our next phase. So that brings us to the last phase of the methodology, the schema design pattern. What we need to do is identify we have a need for them and just apply them. So I've grouped them into different families. I have 16 active patterns right now into 5 different categories. I'll describe some very quickly as we go through the example. So one is called the extended reference pattern, and it's an in-between solution between embedding and referencing. Sometimes you feel that you need to do a join in order to get a piece of information. Think of like a lookup or something like that. If you're going to embed all that, it may not be good because you're bringing a lot of information you don't need. Or what if you still keep a reference to that, but you just bring the little piece of information that will prevent you to do the join that is the most frequent operation. So in this case, in my article, if I bring the name with the ID of my writer, I don't have to do joins for most of the time that I just want information about the article. If I need more information about the person, then I can go fetch it. So that's what we call the extended reference pattern. The other one is called a computed pattern. Think view. But the benefit in MongoDB in the document model is you can take that result of a computation and put it at the right place. In this case, we have an array of comments, and I want to know how many total comments. I can put it directly at the right place where the one-to-one relationship is with its entity. In this case, it's an article, so the counter of comments will go inside the article. And again, we have a lot more information in the blogs about all those patterns. Subset, I want to show an article. I want to show maybe the last 10 comments I have on it, or the 10 most popular. So instead of embedding all the comments, which could be in the 1,000, what I can do is just bring a subset of them, which often can be done in conjunction with the extended reference to bring not even all the information. And finally, putting the schema version in the document. And that's going to bring us to the last pattern. So this one is called schema versioning pattern. The change in the schema is simple. It's just a schema version. What really makes it stand apart is all the operation that you can do around it and what it brings you in terms of benefit. So any successful system will go through changes, likely including data model changes. If your product lives for a few years, you're going to have those. Typical modifications are, I'm just changing the field. That works very well with relational database. You just do an alter table, that's it. But if you modify a relationship, that becomes a little bit more complicated. If you were in a relational database, let's say we go back to our example here. We have some users. They have a home phone number and a work phone number. And in those years, I thought these were the only two ways I could communicate with someone. But then obviously I was wrong. Now these days, you have Skype, WhatsApp, name it. There's probably a new one tomorrow. So I decided that I want to represent that as a one-to-many relationship with the communication mode. So in a relational database, I was going to do that migration. It will look a little bit like that. On Friday evening, I have my one table. I'm going to bring the system down. I'm going to reformat my data to create a new table, migrate data in, and then I'm going to reopen the service. Now let's do the same with MongoDB. I have the structure, and that really doesn't really fit, so I figure out, well, maybe I'll have a communication array, which could be also a separate a collection if I wanted, but in this case, it makes sense to have it there. It would be the same result. And we're going to have the version number. Now, this is not a content version number. It's a schema version number. So it tells you this document in which shape it is versus the schema that you're keeping. And the nice thing here is you piggyback on polymorphism. You use the fact that MongoDB can have documents in different shape to have those documents existing at the same time. So on Friday, I have these 3 documents. And then on Monday, I want them to be in version 2. So I'm going to go and migrate them one by one. Now, the key here is as long as the application is able to read the documents in the 2 shapes, I don't need downtime. I just have documents that have different shape, and each document carries its own version schema. So when I read the document, I see the version. I can send it to the right piece of code that knows how to process it, how to display it, how to do whatever I have to do with it. So I don't need downtime. So MongoDB not lets you just develop and deploy quickly, but also evolve your application and your schema quickly. So I divided the presentation into 3 sections. The need to model. So some of the key points we get out of that, it's imperative to know the features of the product you use. And the optimal grouping of objects into collections is determined by the workload. So that should be the thing that you start with when you want to do your data model. Or techniques to model, we can best act on new hypothesis if we know the original hypothesis. So write down what your system is supposed to do and track differences. And the main thing, if you have to remember one thing from this presentation that's going to guide how you would build your model, is what is used together in the application is stored together in the database. And we finally talk a little bit more about evolving the model. Any successful system will go through changes, likely including data model changes. And MongoDB lets you develop and deploy quickly, but also evolve your application and schema quickly. So we talk at the beginning the fact that maybe things change, maybe a feature didn't exist, now it's going to exist, and you need to modify your model. You can feel in good hand that with MongoDB, you can go with a model and work with it for a while, and if things change, you'll be able to make the changes to it without having downtime, and relatively easy, so you'll get clean changes in your model. To learn more, the book I presented at the beginning has the latest rendition of all the patterns. In the next months, I'll be working on updating the blogs, the pattern blogs, to include the new patterns that I have, and one has been renamed and add some information there. And we also have the MongoDB University, 2 main classes if you want to do data modeling. The first one is not really data modeling per se. It's called MongoDB for SQL Professional. So if you're coming from the SQL world and you want to understand MongoDB and you feel that you have to relearn everything from scratch, that's not the case. MongoDB is still a database. There's a lot of things that work exactly like Oracle and the other databases. So what this course is trying to do is to map your knowledge from what you used to know in the relational database to MongoDB. And then we have the full-fledged data modeling class called M320 that we're in the process of redoing like right now. So thank you, everyone. Looks like I ran out of time here. So I won't be able to take questions, I think. But I'll be around in the next hour or so. I do have some reviews to do, but the time I'm not in a review, I'll be there. And for sure, I'll be there for the beer. You know, especially being in Germany, there is no way I'm not going to have my beer here with you guys. So I'll be waiting for you, the one who are passionate about data modeling and wants to come discuss things. That should be fun. So thank you again for having us.